to our second lecture on this atmospheric flows. Again, it is on introduction. First of all, we are trying to collect a lot of technical jargon, names, and so on. That is in some sense important when we want to really go deeper into those details, try to apply mathematical principles, try to work out or solve these differential equation and so on. It's okay. We write some equation, we put some boundary conditions, we make some kind of approximations and so on. But at the same time, being science students, we should be in a position to really understand the common names, what people use it, perhaps the technical guys, scientists use it, that also we should be aware of. Though the name may not really have that much big importance, but typically it becomes easy, more like a language to communicate. Something like polar jets, subtropical jets, mid latitudes, and so on, so kind of technical jargon. And now what we are trying to see is a common phenomena what atmospheric science students try to observe or learn that. That kind of common terminology we are also going to begin with. Instead of going through PPTs and so on so stuff, we will visualize some animations, videos, try to get feeling for that word. Maybe what it means that polar jet, maybe what it means that polar cell, and so on, so kind of things. So let us begin. So yesterday we tried to really look at some of the planets, their flows and so on. So in today's class also we will try to continue with that. Once we are done with those extraterrestrial planets and so on, then the ground reality like coming back to Earth, try to understand them. That is the way we go ahead. So what about Mars? Anyone can answer? What kind of weather system they have? What kind of climate, flows, and so on? What kind of conditions they experience?
So the atmosphere is pretty thin as far as I know. But they
Okay.
have polar caps on North and South Pole, so they melt or they sublime during the summer season. They create some currents, I think.
Wonderful, wonderful. With whom I'm speaking? Pawan?
Sir, Harshendu, sir.
Harshendu. Okay. So let us look at it. But Mars is famous for what?
Red star.
It's a iron-rich soil.
Red planet, sir.
Any other interesting, funny, hilarious?
I know it is
The
called red
tallest,
planet.
tallest
No.
mountain in the solar system.
Okay, the girl is saying something else.
Alien.
Sir, it's satellite, sir.
No, man. Men are from Mars. Okay, let us look at it.
Mars, you probably wouldn't think that it looks like a very nice place to live. It's dry, it's dusty, and there's practically no atmosphere. But some scientists think that Mars may have once looked like a much nicer place to live, with a thicker atmosphere, cloudy skies, and possibly even liquid water flowing over the surface. So how do you go from something like this to something like this? NASA's Maven spacecraft will give us a clearer idea of how Mars lost its atmosphere, and scientists think that several processes have had an impact. One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. In our solar system, the sun constantly emits high-energy photons. When one of these photons enters the atmosphere of a planet, it can crash into a molecule, knocking loose an electron and turning it into an ion. Ions by themselves don't do much, but when a magnetic field is nearby, they'll spin around the field, spiraling in the field's direction. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. The part of the field that just grazes the planet can easily pick up a bunch of ions and launch them out into space. If the field happens to be in just the right place, however, it might pick up ions and fling them right back into the atmosphere at up to 1,000 kilometers per second. The ions can then crash into other molecules and fling atoms everywhere like a cue ball in a game of pool. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. And over billions of years, this could have caused quite a bit of change, especially since the solar wind may have been more intense early in our solar system's history. Scientists think that all of this may have caused Mars to gradually transform from what may have been a very nice place to live into the dry, dusty world we know today. And Maven will study this process and tell us how it really works.
So what about atmosphere? What did you understand from this Mars atmosphere? Is it too fast? Hello?
Yes, sir.
Yes, would you like to summarize it?
Sir, they were saying that due to these solar flares and winds, the ions in the atmosphere they got picked up and they got blown over. So maybe Mars had a good atmosphere back in the day, but over the years it got blown away. So there is not much left over there.
Fine. Great. So what should be the next planet, if that is the case?
Venus.
Wow, man, Harshendu, remarkable. So naturally we have to go for equality. That's obviously Venus.
Named after the ancient Roman goddess of beauty, Venus is known for its exceptional brightness in the night sky. But behind this facade is a world of storms and infernos unlike anywhere else in the solar system. Venus, the second planet from the Sun, is very similar to Earth from a distance, but up close, it's a very different world. Venus is about the same size as Earth, just slightly smaller. Its structure is also nearly identical, with an iron core, a hot mantle, and a rocky crust. The crust of Venus, however, is dotted with thousands of volcanoes, including Maxwell Montes, a volcano almost as tall as Mount Everest. Venus also has a thick, layered atmosphere. It's full of clouds that rain sulfuric acid and whip around the planet at speeds up to 224 miles per hour, faster than some Category 5 hurricanes. The atmosphere is so thick that it creates a surface pressure similar to what it would be about half a mile deep in the Earth's oceans. This pressure is heavy enough that a human standing on Venus's surface would be crushed. The atmosphere is made of greenhouse gases, primarily carbon dioxide, which create an extreme case of global warming. They trap the sun's heat, causing surface temperatures to rise over 880 degrees Fahrenheit, making Venus the hottest planet in the solar system. Venus is so inhospitable, neither humans nor spacecraft are able to survive the planet's surface. But some scientists speculate that Venus wasn't always so unwelcoming. From roughly 2.9 billion to 715 million years ago, global temperatures on Venus may have been just a few degrees cooler than Earth's are today. And scientists theorize that the surface may have contained shallow oceans that could have held enough water to support life. Today, life may still exist in Venus's atmosphere. About 30 miles up in Venus's clouds, where the temperature and surface pressure are similar to those on the surface of Earth, scientists have observed strange dark streaks that appear to be absorbing ultraviolet radiation, a phenomenon that could be evidence of microbial life. Life may struggle to survive in the atmosphere of Venus, but it is this unforgiving environment that's made Venus an icon of beauty. It reflects 70% of all the sunlight that reaches the planet, which is why Venus shines more brightly than any other planet or star in the night sky. While more than 40 unmanned spacecraft have visited this infernal world, Venus, so illuminated in the darkness of space, still has much to reveal.
Great. So how about coming back to Earth? So let us look at few phenomena. Maybe the first step to know about any atmospheric flow, planetary flows, and so on is it something like randomly gas molecules are distributed in space, or is there any structure, ordering of these molecules? In some sense, the easiest way of looking at those layers is the first step, and that's the thing what we are trying to look at.
Sir, sorry to interrupt.
So we will see that later, how this troposphere or pass, at that pass, there will be a lot of mixing happens, and that can really generate polar vortices and so on. Usually we think that the second layer is more of a stratosphere, is stratified thing. Nothing interesting happens, but there are lots of mixing really happens, and that can really create very big scale vortices. We'll come back to that. It's not just troposphere related atmosphere, but there is something very interesting happens at those passes. We'll come back. Let us watch that layers.
The sound is there.
Sir, the sound
Yes.
is not coming. Video sound.
There is no sound. I think it's just music.
Okay.
So it's all based on temperature. First 10 kilometers above or maybe within that zone, your aircraft really flies. So your ozone layer will be in the stratospheres. This is stratified environment. We will come back what it means stratified. So mesospheres, meteoroids, all these things really burst out. And it is really coldest. Your ionic currents, all these things happens there. So all the way 1000 kilometers from Earth's surface, you can really count it like thermosphere, atmosphere in some sense present. Any entry vehicles, all these kind of things, in case if you want to really come back all the way, you have to come through that layers. So the dynamics in these layers completely different. Though you can write is something like partial differential equations, stochastic equations, maybe molecular dynamics and so on, so kind of stuff. Each layer, in some sense, the model is different. Perhaps solving them or trying to understand, it shows rich science. So for second phenomena, we will see that once we understand that there are something like based on temperature, 4 layers. Tropo, strato, meso, thermo kind of things. Natural question is, let me look at this troposphere. Something like I sense winds are blowing, what it means. So which country is famous for windmills?
Netherlands, sir.
Great, great. But any idea what is the use of windmill?
Generate electricity or power.
We'll see that. So warm, guys, am I audible?
Yes.
Yes, sir.
Yes, sir.
So air gets warmed and it wants to rise. Because of buoyancy, these layers start rising, creates low pressure locally, and some other location it's not that warm enough. So relatively that is high pressure. So land portions are easy to get warmed up. So because of that, this air also wants to rise up there. So this is all relative terminology, low and high. And we usually associate this kind of phenomena at large scales, not like locally, maybe in my room, my body is continuously radiating heat or perhaps convection motions happening. And maybe next door, air might be a bit cooler and it may be trying to reach me, can happen. But we usually don't associate with this kind of big atmospheric flows and so on, so kind of thing. You really require such kind of magnitudes, heating up to very large areas and really pushing all this air to go up, so that relatively some other air, colder air really comes there and wind blows and so on, so kind of thing happens. If these are very small scale kind of events, perhaps your air which wants to come from high pressure to there, the dynamics might be completely killed by local viscosity of that air. It may not really even try to penetrate, push and come towards you. And already within that layers itself, it is stratified, so it may not be in a position to really move. So all these phenomena, what we are talking in a very vague way, applicable at certain cases, not at other cases. Usually at very large scale, so one can deduce orders of magnitude analysis clearly, like when to apply, when not to apply and so on. But if we are really jumping into that kind of picture, it really, we mess up with the things. So instead of that, in a hand waving way, what we are trying to look at is maybe warm air rises up, cold air really comes and wind blows. So shall we move to the next? Okay, let's look at. So these are called hot spots, and those are the zones where thermal plumes try to rise. But they carry moisture also. While they are going up, cool, condense. They attract many nucleations by agglomeration and so on. So what is the typical weight of these clouds from this video? What did they mention? 500 tons, and how many elephants?
100.
100 elephants. If they are of that heavy, why they are not falling down?
Spread over a large volume.
How does that really matter for weight?
Density.
More buoyant than air.
They are buoyant than air. The complete cloud or individual things are. I mean, my weight is something like, let us consider 65, 70 kgs, and maybe let us consider I might be in the 3rd floor, 4th floor, or maybe I'm trying to drop down from aeroplane, but I will fall, but clouds won't fall. My weight is just 80 kg force, but there it is something like 100 tons.
It's like Archimedes principle will come into picture. And the amount of the fluid that they are displacing is more than the weight of the clouds. So that's why
So if we are
specific
go ahead.
Yes.
So basically, yeah. So basically, it depends on how we are going to mathematically model it. If we are going to model it in that way, like it is very big thing and everything is closed, the cloud is more like a fabric and not interacting with ambient and so on, so kind of stuff, it occupies a lot of volume, lower density and so on, so kind of thing, it works. It's just a kind of mathematical model what we use, which we usually call partial model in atmospheric flows, where this entire object hardly interact with outside things, even if it is trying to move down, up and so on, based on your Archimedes principle, like how much it really displaces, what kind of buoyancy force happens and so on, so thing. If you are looking at microscopical level, it contains a lot of water molecules, ice crystals and so on. These are so tiny objects. Some of them really wants to come down, but neighborhood air, what it says that, see, I'm offering you viscous forces. Even you are a bit heavier than me, you cannot really penetrate into that because large amount of air through which you have to pass. So as a drag, what I'm going to do is I'm going to stop you. At the same time, the temperature within the system or buoyancy, whatever it is there in the system, in terms of relative terminology, what we are trying to talk about, is says that, hey, because we are more or less at the same kind of temperatures, or perhaps you might be at higher temperature, you might be at lower temperature, you might be less buoyant, you might be higher buoyant. So I can really create some kind of buoyancy force on you, or maybe I can really create weight on you. So you fall down or you rise. All these motions, in some sense, arrested by local flow motions. Because of that also, clouds are the individual particle, they want to really come down, but they will be halted. There always be if you are really zooming into microscopic levels, these are always be charged kind of particles. They try to balance their charges, they try to arrest it. You may not see something like a string attached to particle, but because of these attractive forces also, if someone wants to go down, other one immediately create a repulsion, it says that you stay, don't go. So it's such a complicated, messy situation to understand these clouds. The very hand-waving kind of arguments, what we can really understand is maybe it's more like Archimedes kind of principles. That's the reason even it is having such kind of 100 tons of kind of thing on overall that maybe at each and every local location may be buoyant enough so that they might be floating. Is really complicated stuff. Let us go further. How many types of clouds are there? How to characterize them? Clouds play very, very big role. All the time we see clouds, we hardly care about it. For fluid mechanics, for weather, for atmospheric flows, even to model mathematically what happens to these dynamics, big atmospheric circulation, clouds play damn important role. Any idea about clouds? What kind of types and so on? Coral guys.
Cumulonimbus.
One at a time. One at a time. If someone is speaking, don't interrupt them. You just mute yourself. Yeah, go ahead.
So 3 types, sir.
Okay. What are they?
Cumulus,
okay.
stratus, nimbus.
Okay. How to define that kind of names? Short boy, medium height, tall. What is the criteria for that?
Height, based on height.
Based on height formation. Okay. Any other?
So height and darkness also, color also.
Color. Okay. How does it matter? Color?
Color, it will tell us the amount of water content and the cloud is having.
Okay, fine. Any other thing? Referring to different kind of clouds based on their height, content, and different kind of characteristics, the way how they behave and so on. So I think people have different kind of Latin names. And the main role played by the clouds, they mainly, okay, one is your rain formation, bringing water from one location to other locations, having vegetation, supporting life and so on, so thing, forming rivers, streams and so on. The second thing is the harmful solar radiation will be mostly reflected out. Your clouds behave like semi-transparent mirrors. Any harmful radiation that will be really reflected out, and remaining things whatever required for support of life, those, hello?
Yes, sir, you are audible.
Yes, sir.
Okay, I'm audible.
You are audible, sir. Audible, sir.
And that is the big role played by these clouds. And long term is not just about today's weather, but long term climate. Maybe after 40 years, 50 years, 100 years, how Earth will be, what kind of things happens, mainly governed by your clouds. So let us move on to a new one named greenhouse effect. Any idea about that?
Trapping the reflected radiation from the sun's
Wonderful.
surface.
Wonderful. So let us look at that video.
What is the greenhouse effect? Earth is a comfortable place for living things. It's just the right temperature for plants and animals, including humans, to thrive. Why is Earth so special? Well, one reason is the greenhouse effect. A greenhouse is a building with glass walls and a glass roof. The clear glass allows sunlight to shine into the greenhouse while also trapping the sun's heat inside. This is how a greenhouse keeps plants warm even at night and in the winter. The greenhouse effect keeps Earth warm in pretty much the same way. Earth isn't surrounded by glass, but it is surrounded by a jacket of gases called the atmosphere. In the daytime, the sun shines through the atmosphere, warming Earth's surface. After the sun goes down, Earth's surface cools. This releases heat back into the air, but some of that heat is trapped by the gases in the atmosphere. These heat-trapping gases are called greenhouse gases. Carbon dioxide, water vapor, and methane are all examples of greenhouse gases. Earth needs a balance of greenhouse gases to maintain just the right temperature for living things. But some human activities are changing Earth's natural greenhouse effect. For example, burning fossil fuels like coal and oil releases more carbon dioxide into our atmosphere. These extra greenhouse gases can cause the atmosphere to trap more and more heat, leading to a warmer Earth. NASA satellites are constantly measuring the gases in our atmosphere from space. They've observed increases in the amounts of carbon dioxide and other greenhouse gases. The information from NASA satellites can help scientists figure out where greenhouse gases are coming from and how they are ending up in our atmosphere. This information will help us better understand the impact that greenhouse gases have on our climate and help us better understand this very special greenhouse that we call home. Find out more about our Earth at NASA Climate Kids.
Great. Something, a phenomena, I don't know, maybe for coral guys it's obvious, but other guys, it might be a bit strange thing, something named jet streams. People are crazy about understanding. What we will see is something like banded patterns we will see. The whole point, what people try to understand about that is that band won't be something like a very nice smooth, but there will always be hydrodynamical instabilities created in that. It starts showing particular kind of wavy format. People try to really analyze why that kind of instabilities happen, whether that bands really go here and there and so on, so kind of stuff. And that has a big impact on long-term weather forecasting or even on climate. That's what we call jet streams. These mainly happen around 6 to 12 kilometer kind of height, where your planes really try to fly, the commercial planes and so on things. And especially there are people found some 3-4 zones, above 3 zones, below 3 zones kind of thing on that earth. So here what we are trying to see is equator and pole. So it's more like a cut sectional view of earth sphere, whatever that you want, you are going to see from equator. Along that earth surface, if you are going to see, you reach poles. That if I am really convert into rectangular framer, like the curved one, I twist it so that it becomes a rectangle. So at equator, these clouds, air really rises because it's warm layers and so on, so thing. They rise and try to create something like Hadley circulations. And again, there will be something like poles where air really comes down, create polar cells. In between that, there will be Ferrel cells created because of mass continuity kind of dynamics. This kind of additional Ferrel cells happens, where this intersection of polar cells and Ferrel cells happen, and also where Hadley cells and Ferrel cells happen, you start seeing something like a green patchy kind of stuff, where circulation, fluid circulation happens. Those zones are called polar jets, stratotropic kind of jets. So basically what you are seeing is fluid go round and round, and around the earth it will be tied up like a rope. So what you are seeing is a cut sectional of that rope. That rope goes all the way around earth. That if we would like to really have visualization, this subtropical jet around the 30 degrees on the north side, similarly on the south side happens, that goes around this periphery of that earth. Around some 6 to 12 kilometers kind of height happens. And these polar jets are quite close to earth, something like around 5-6 kilometers kind of height. And the subtropical jets are something like where commercial planes really fly on that equator.
What's going on? Well, it's all to do with the jet stream, as is often the case. The jet stream at the moment.
Talking about the jet stream and its position has become more commonplace in weather broadcasts. It is often blamed for why we get the weather we do. But why are we so interested in it? And how does it influence our weather? A jet stream is another name for fast-flowing currents of air that encircle the globe at high altitudes. The major jet streams are the polar front and subtropical jets. They can reach speeds over 200 miles per hour, but this speed is not constant throughout the length of the jet stream. Embedded within the wave-like pattern of the jet stream are localized areas of even faster winds. Even though these areas are relatively small-scale features within the larger jet stream, they are important as they provide a focus for modifications to surface pressure patterns. Their position within the trough ridge pattern of the larger jet stream influences the resulting shape and can affect the development of weather at the surface. A stronger jet on the left or rearward side of a trough will cause that feature to sharpen or extend. A sharper trough can cause deeper low-pressure systems at the surface, giving stormier weather. For a ridge, this same position of the stronger jet will cause the feature to amplify. An amplified ridge can block the normal west-east progression of weather systems and bring more prolonged periods of settled weather. On the other hand, a stronger jet on the right or forward side of the trough will cause that feature to relax. For a ridge, this same position of the stronger jet will cause that feature to decline. Both circumstances have less impact on the development of surface weather systems. Jet streams affect the weather by generating regions where air ascends or descends, which can lead to areas of falling and rising pressure at the surface. Certain regions of jet streams are more favourable for rising or sinking air. To explore this, let's take a journey through a simplified jet stream in the northern hemisphere. Two isobars, lines of constant pressure, are shown on a horizontal surface. High pressure lies in the warmer air to the south, and lower pressure lies in the colder air to the north. The isobar spacing is closest together at the centre, showing the region of the strongest pressure gradient and stronger winds. Before air moves into the stronger jet entrance, it is subject to a balance of forces, known as geostrophic balance. This is a balance between the pressure gradient force, which acts from high to low pressure, and the Coriolis force, an apparent force that is the result of the Earth's rotation. As the air enters this region, it accelerates because of the increased pressure gradient. To maintain the balance, the Coriolis force would also have to increase, but its response is not immediate. This means that whilst the overall movement of the air through the jet stream is still eastwards, there is now a component towards the north. This northwards component is the ageostrophic wind, which results from the imbalanced forces. In the entrance region of the stronger jet, this component causes the transfer of air from the right side of the jet entrance to the left side. This removal of air from the right entrance creates an area of upper level divergence, whilst air piling up in the left entrance region of the jet creates an area of upper level convergence. These areas of divergence and convergence have a significant influence on surface pressure and the weather we experience. Diverging air at high levels means that the air in the column is being depleted. To fill this depletion, air from below rises. If this region of diverging winds is stronger than the corresponding converging surface winds, there is an overall loss of air from the vertical column. As pressure is the weight of air in a vertical column, if the amount of air decreases, the surface pressure must fall. This would cause an underlying surface low pressure system to deepen, bringing increasing wind speeds and heavier rain. For an underlying area of high pressure, this situation will cause surface pressure to lower, lessening its blocking effect and allowing the eastward progression of weather systems. For the left entrance region, where air is piling up, there is an overall increase in the mass of air in the vertical column, and so surface pressure must rise. This would cause an underlying surface low pressure system to fill and weaken, bringing decreasing wind speeds and less unsettled weather. Pressure in an underlying area of surface high pressure would get even higher, continuing the settled conditions, but also increasing the risk of visibility problems caused by haze, mist, or fog. Our journey now takes us to the core of the stronger winds, where the Coriolis force is caught up with the increased pressure gradients, and geostrophic balance is restored. However, this balance is short-lived as air starts to decelerate in the widening pressure gradient in the exit region. Again, the Coriolis force is slow to respond, creating an imbalance. But this time, the Coriolis force is larger than the pressure gradient force. This now creates a southwards component of ageostrophic wind. This southwards component now causes the transfer of air from the left side of the jet exit to the right side. So air is now piling up in the right exit region, creating an area of upper level convergence, sinking air, and surface pressure increases. And air is leaving the left exit region, creating an area of upper level divergence, rising air, and surface pressure falls. When focusing on the regions of jet streams that are most likely to cause a larger impact in the weather that we experience, meteorologists look for the right entrance and left exit regions. When these upper level development regions coincide with favourable surface features, such as low level temperature or humidity gradients, we experience the three-dimensional nature and interdependencies of our complex and interesting weather.
So there's a lot of technical jargon going on. During our course, we will learn about what it means these geostrophic balances, azeotropic, what it means Coriolis, how these relations really work and so on. For that, we have to really learn math. That we will go step by step. We should really write the dynamics, try to simplify that, understand which term really dominates what, how these systems really behaves and so on. We'll come back. But it just gives us a little bit motivation like, okay, there is something going on, a lot of terminology, but to understand that there is something like conservation principles, we will write it and try to learn it. Let us look at that.
My PhD journey, starting in 2013 and finishing in December 2018, then you'll have seen what I have been studying. You've seen how I have studied it. But I want to, in this video, definitively set out what I found and what ended up going in my thesis. And thanks to Dashlane for sponsoring this video.
So Simon Clark is the one who is talking.
To stop people from feeling lost, I've broken it down into sections. Let's start with some background. So my PhD was about the Earth's atmosphere. Like ogres, like onions, the atmosphere is divided into layers. From the bottom up, you have the troposphere, the stratosphere, the mesosphere, and the thermosphere. These layers are most commonly defined by their temperature profile, how temperature changes as you go higher up. In the troposphere, the temperature gets colder the higher you go. If you've ever been up a mountain, you'll have felt this effect. However, once you go past about 10 kilometers above the surface, the temperature stays the same and then actually increases with altitude. This happens until you hit about 50 kilometers up, at which point the temperature starts to decrease with altitude again. This region is called the stratosphere, and it behaves very differently to our layer of the atmosphere, the troposphere. The largest feature of the stratosphere is the polar vortex, a circulation of fast-moving air over 1,000 kilometers across, with wind speeds of over 200 kilometers per hour, that forms every year in the winter over the Arctic. My PhD was about how these two layers interact with one another, in particular during big violent events called sudden stratospheric warmings. A sudden stratospheric warming occurs when the polar vortex breaks apart, either because it split in two or because it moved too far south. These events are called warmings because when the vortex breaks apart, air from further south piles into the stratospheric Arctic and squishes it down. This squishing, or more properly, adiabatic descent, results in increases in temperatures of up to 70 or even 80 degrees Celsius in the stratosphere over just a couple of days. And we've known since about the year 2000 that when sudden stratospheric warmings happen, the weather in the troposphere is affected for up to 2 months. Storms going across the Atlantic track further south than normal, and there's an increased chance of extreme cold in mid-latitudes. This happens because the primary mode of variability in the stratosphere is the strength of the polar vortex, while the primary mode of variability in the troposphere is the location of the jet stream, the fast-moving river of air that provides cold Arctic air from warmer mid-latitude. And these two modes of variability are coupled together, which we can describe mathematically by an Arctic oscillation index, which is just a number which can be defined at any height above the surface. If the AO index is positive, the polar vortex is strong and the jet stream is relatively straight and far north. If the AO index is negative, then the vortex is weak and the jet stream is wavy and further south. In the aftermath of sudden stratospheric warmings, we see descending negative AO index anomalies, the influence of the sudden warming creeping towards the surface and staying there. So a vortex breaking apart results in a very wavy jet stream, which sits further south. We know that this happens, but we don't know how this happens. My PhD was about proposing a quantitative mechanism for this descending influence. And in order to explain exactly how I did that, I first need to give you two more pieces of specific background information. The Arctic Oscillation Index is a result of a complex statistical process called Principal Component Analysis, or PCA. You don't need to understand how this works, but the end result is important. When applied to surface pressures over the northern hemisphere over a couple of years of data, PCA defines a pattern over the year. This pattern explains where the majority of variability in surface pressure takes place. For example, it shows that if pressure over the Arctic is relatively high, the pressure over the North Atlantic is relatively low, a bit like a seesaw. This is the Arctic oscillation pattern, and the AO index is the number that tells you if the seesaw has one end up or the other, in terms of the pattern, whether the Arctic pressure is high, and so Atlantic pressure is low, or if the Arctic pressure is low and the Atlantic pressure high. The first step in my PhD was simplifying how we represent these variations in surface pressure. For reasons that will become clear in a second, I was specifically interested in pressure over the Arctic. So I defined a new pressure index, designed to be equivalent to the AO index. It was designed to be simple to make. You just average the pressure over the area north of the 65 north latitude line, and then subtract the long-running average to produce a pressure anomaly over the Arctic. But is this equivalent to the AO index? Well, if you compare the Arctic oscillation pattern to where my index is calculated, you see that my index is defined over the same area as the primary blob of the AO pattern. And because the AO is a seesaw pattern, if you know whether one side of the seesaw is up or down, you know if the other side is down or up. So my index contains the same information as the AO index, but in a simpler way. And this is something which I demonstrated statistically. So I defined a new index to represent the principal mode of variability in air pressure. But why was that important to do? Well, I defined the index in such a way
that I could easily derive equations that govern how it varied in response to changes in the rest of the atmosphere. So remember what I was trying to do? I was trying to show how the strength of the polar vortex varying could change the position of the jet stream in the troposphere. If I could derive a set of equations which showed how the pressure index in the troposphere varied in response to changes in the stratosphere, then I will have achieved that. You can think of my index as like an imaginary cylinder of air surrounding and above the Arctic. The pressure anomaly in a particular slice of this cylinder has the same information in it as the complex PCA-created AO index. But while that index has lots of things that influence how it changes in time, my pressure index has just two things. The mass of air that goes through the cylinder's walls above the slice, and the mass of air that moves vertically through the slice. If air moves horizontally into the cylinder above, then there will be more mass on top of the slice of cylinder, which will increase the pressure on it. Likewise, if air moves vertically up through the cylinder, then the pressure on the slice will also increase. What I needed to do then was derive two equations. One that describes the air mass that moves horizontally into the cylinder, and one that describes the mass that moves vertically in the cylinder. These are those two equations, and they were the next important thing I did in my PhD. If you want details of how they're derived, then read my thesis, link in the description. For this video, I need to explain the most important variable in these equations, psi, the stream function. A stream function is a way that we can mathematically describe a fluid flow. The atmosphere behaves like fluid on a rotating sphere, and so we can define a stream function for the atmosphere. A stream function is a scalar field, meaning that it has a single value at every point in the atmosphere. The speed that the atmosphere flows in the east to west and north to south directions, otherwise known as wind, is calculated by looking at how much the stream function varies in the north to south and east to west directions, respectively. You can also calculate the temperature of the atmosphere at a point by looking at how much the stream function changes as you get higher in the atmosphere. So by calculating the gradient of one field, the stream function, you get information about multiple fields, wind and temperature. I used the stream function to calculate the air mass moving into and within the imaginary cylinder of air around the Arctic via these two equations. But I've only told you what the stream function is, not how you calculate it. And that's really a video all on its own. But basically, you use a variable called potential vorticity, or PV for short, which might sound familiar to long-term viewers. PV is another scalar variable that's rich in information about the state of the atmosphere. It's not a physical thing that you can see or feel, but constructed from how air rotates and how temperature changes with height. Via a process called inversion, you can take a PV distribution and get a stream function from it. The PV can be in just one part of the atmosphere, and yet the stream function you get by inverting it is defined everywhere. So the stream function associated with a PV distribution in just one area encodes information about how that area influences the rest of the atmosphere. This has been a few conceptual leaps one after the other, so just to recap, PV is a variable in the atmosphere, which you invert to get a stream function, which describes how the atmosphere behaves. This stream function can be used to calculate how air mass gets moved around in the Arctic, and those mass fluxes used to calculate changes in my pressure index. PV calculates a stream function, which calculates mass fluxes, which calculates changes in the pressure index, which tells us whether the surface atmospheric seesaw is up or down. If I could show that changes in the PV distribution in the stratosphere caused changes in the pressure index at the surface, then I would have achieved my goal. But I found something a bit different. Not what I expected. You can add together the stream functions calculated from inverting different PV distributions in different places in isolation to get a total stream function. If you've studied electrostatics, this will sound familiar. It's just like the superposition of charges. And remember that PV encodes information about the area of the atmosphere it's defined in, transmitted by the stream function to the whole atmosphere. So if you invert the PV in the stratosphere on its own, you will get a stream function which tells you how the stratosphere influences the rest of the atmosphere. I could define a stream function
psi s, which only has stratospheric information in it. It's calculated by inverting stratospheric PV only, and then use this stream function in my horizontal and vertical mass flux equations to see how the stratosphere influences the pressure index in the troposphere. And I could equally define a stream function psi t, which is calculated by inverting PV from the troposphere on its own, and then use that in my mass flux equations. Combining the two stream functions together produces the total stream function, and so the total horizontal and vertical mass flux. However, by considering the stream functions separately, you can isolate how much horizontal and how much vertical mass flux is forced by changes in the stratosphere and how much is forced by changes in the troposphere. My theory was that in the aftermath of sudden stratospheric warmings, the vortex splitting apart, that the stratosphere had a strong influence on the troposphere, communicated via mass fluxes induced by changes in the stratospheric PV distribution. Man, it literally took this entire video up until that point to be able to say that sentence and have you understand what it means. I could test my theory by calculating the total mass fluxes moving into and within the imaginary Arctic cylinder of air via my equations, and then comparing that to the mass fluxes seen in observations. If the total mass flux predicted by my equations matched those seen in observations, then that would verify that my equations were correct. And if that was the case, the relative sizes of the two contributions from the stratosphere and from troposphere will tell me if the stratosphere has a significant influence on the troposphere. So, was I right? This is an example time series of my pressure index as seen in observations. The horizontal axis is time, and the vertical axis is height above the ground. You see descending positive and negative pressure anomalies over the Arctic. Now compare this to what I calculated using my equations. At first glance, they don't appear very similar, but you start to see similarities between the two. This large negative feature followed by an ascending positive anomaly. This large positive anomaly encompassing a negative anomaly, all of which are approximately the right magnitude. If you do the stats, the two time series from observations and calculated by equations are reasonably close to one another for the past 40 years of data. They correlate moderately. I'll spare you the exact details of why this doesn't work perfectly, but the basic reason is that you're trying to sum up lots of things which are positive and negative to try and make something which is very nearly zero. And that's open to a lot of errors, especially when using coarse resolution data. If you're willing to accept that these two are close enough to one another, then you can examine the contributions from the stratosphere on its own and from the troposphere on its own. Clearly, the influence of the stratosphere doesn't really get past the tropopause, the barrier between the troposphere and the stratosphere. But, this is cool, eagle-eyed viewers will have noticed that something is missing. Take another look at these two equations for the horizontal and vertical mass flux. The vertical mass flux equation is a linear function of the stream function used, meaning that the stream function never gets multiplied by itself. A bunch of stuff happens to it, but it only appears once. The horizontal mass flux equation, however, isn't linear. It has a psi times a psi. Here, it's a non-linear equation in psi. That means that while you can add together the vertical mass flux contribution from the stratosphere and the vertical mass flux contribution from the troposphere to get a total, you can't do that for the horizontal mass flux. To get the total contribution, you add up the contributions from the stratosphere and the troposphere, and then add an interference term, which has both stratospheric and tropospheric information in. So just to reiterate, because this equation is non-linear, when combining contributions from two different stream functions, you have to add an interference term to the sum, representing the interaction of those two stream functions. If you add that interference term to the stratospheric influence, represented using psi s star, then you see the influence of the stratosphere penetrating into the troposphere. Or in other words, the non-linear interaction of stratospheric and tropospheric information allows for changes in the stratosphere to affect the surface. And while this is just one example time series, the overall statistics for the 40 years of data back up this conclusion. So speaking mathematically, I demonstrated that the non-linear interaction of stratospheric and tropospheric information
substantially force Arctic pressure tendencies in the troposphere, which is equivalent to saying that they substantially force the AO index in the troposphere, or surface weather. And that's not something which we'd known before. And it was something which was only possible to learn because of the entire framework that I constructed in the thesis, from the pressure index to the mass flux equation. I realized that this video is a relatively deep dive with lots of new concepts and not very much time. So in case you got lost along the way, let me rephrase what I learned in my PhD without referencing any of the maths. I learned that the stratosphere, that's the next layer up of the atmosphere, can influence the troposphere, our layer of the atmosphere, including weather at the surface, but not directly. Instead, the stratosphere influences surface weather by the way that it communicates with the troposphere. Or, if you like, that the stratosphere can influence the surface weather, but if, and only if, the troposphere is in the right configuration to receive that influence. And this is a relationship which is most noticeable in the aftermath of big events like sudden stratospheric warming, but it holds generally. And that non-linear relationship, the conversation that goes on between the stratosphere and the troposphere, is something that we didn't quantitatively know until my PhD. This video, as long as it is still only a brief overview of what I did in my PhD, and it doesn't even include all the results from my thesis. So if you'd like to learn more about what I did and read it yourself, then I'd at least recommend giving the background chapter a read. Then you can do so on my website. I have a website, by the way. My website is actually protected by this video sponsor, Dashlane. I started using Dashlane a couple of weeks ago on my phone and on my computer and my laptop. And honestly, I have nothing but positive things to say about it. Dashlane is a service that keeps track.
Okay. To put it in this way, we have learned a lot of new terminology and so on, but over the course, we will understand all these kind of potential vorticity and so on, so kind of stuff. And by now you must be understanding what a PhD means also. Something new one has to figure it out, and this is one of the remarkable thesis by on these atmospheric flows, because earlier people used to simulate atmospheric flows just taking something like boundary condition, earth is rotating, so on, so kind of thing. Top layers have something like stress-free kind of conditions and solve it, try to understand that and so on. But what Simon Clark tried to show that is not just by simulations, but something through mathematical analysis. There always be layers which always try to interact with each other, and one has to really take into account that is the one which actually change your climate on long run. Something to deal with is polar vortex, how that's going to really affect whatever those waves which we usually see, something like the jet streams. Earlier, people used to think that these jet streams may be locally modified. That's the reason you have that kind of wandering motions, stretching, maybe more like a river meandering, how it happens. Use something like Kelvin-Helmholtz kind of instabilities, meandering kind of instabilities, and so on. But that's not the reason, but it is something more and deeper into understanding.
The Indian Ocean Dipole, or IOD for short, is a natural and irregular change in sea temperatures across the Indian Ocean. If you think you've seen something like this before, you'd be right. It's very similar to the El Nino La Nina cycle in the Pacific Ocean. In fact, the two are linked, and the IOD can be seen as an extension of, or even a phase of, the El Nino phenomenon. And just like El Nino, the IOD plays a big part in altering weather patterns right around the globe. The IOD changes year to year between three states: positive, negative, and neutral. Each state has different effects on weather patterns, and each year the intensity, or just how positive or how negative the IOD is, also varies. Many years the IOD will simply remain neutral throughout. Generally speaking, the closer a country is to the Indian Ocean, then the stronger the link between the weather patterns and the IOD. The Indian Ocean Dipole is a relatively recent discovery. Scientists have only known about it since 1999, but climatologists have been able to map the pattern back in time due to sea surface temperature observations throughout the decades. Okay, let's look at the phases now and start when the IOD is positive. A positive IOD is when the temperature of the sea on the western side of the Indian Ocean is higher than average. Now, this occurs when the winds at the surface across the Indian Ocean become more easterly, bringing warmer waters to the west. The higher temperatures over the ocean creates warmer air above the surface. That warmer air rises, that lowers the pressure at the surface, and the combination of low pressure and rising warm air generates more rain in this part of the world. Now, it's not just here that's impacted, the whole ocean is, and as well as warming of the waters on the western side, an upwelling of cooler waters on the eastern side of the ocean is created at the same time. And the cooler waters here means that the air doesn't rise as much. Pressure is higher at the surface and rainfall is reduced and droughts. So when the IOD is positive, it usually creates flooding in Eastern Africa and drought in Indonesia and Australia. A positive IOD also leads to an increase in rainfall during the southwest monsoon season across the Indian subcontinent. Now let's look at what happens when we get a negative IOD. A negative phase in the IOD occurs when westerly winds at the surface are stronger than normal across the ocean. And this results in pushing the warmer waters to the eastern side of the ocean and the temperatures in the western Indian Ocean being lower than average. The warming here creates more rainfall in the same way it does on the other side of the ocean when the IOD is positive, and the pattern is totally reversed. During a negative phase, rainfall is increased here, but cooler waters on the western side of the ocean means that rainfall is decreased here. So when the IOD is negative, it can lead to flooding in Indonesia and parts of Australia and lead to droughts in Eastern Africa. It can also lead to a reduction in rainfall during the southwest monsoon season across the Indian subcontinent. Now, in a neutral phase, the sea surface temperatures are around average and the IOD has no impact on weather patterns. In the Northern Hemisphere autumn of 2019, the IOD was extremely positive, the highest ever recorded, in fact. This record-breaking IOD had huge impacts on the weather patterns across many countries. The resulting drought in Australia led to one of the most severe fire seasons on record. And meanwhile, in Africa, the excess rainfall created devastating floods, and the warming seas are also thought to have contributed to a severe locust season here. A recent study suggests that climate change is expected to increase the frequency of these extreme positive IOD years. Now, although the impacts of the IOD are felt more keenly across countries adjacent to the Indian Ocean, just like El Nino, the IOD can affect weather right around the globe. So, does the IOD affect UK weather? Well, actually, the Indian Ocean dipole is just one of many global climate features that affect our weather here in the UK. And we call these our climate drivers. And the teleconnections between them are a really intense area of ongoing scientific research. One connection suggests that a positive IOD can lead to a positive North Atlantic oscillation in late winter. The North Atlantic Oscillation, or NAO, determines how much influence the Atlantic has on our weather. When the NAO is positive, this means westerly winds are more likely across the UK and the weather is generally wetter and windier with a more active jet stream. Although other factors were undoubtedly also at play, this is what was observed in early 2020, with February seeing a number of intense low-pressure systems crossing the country, resulting in the wettest February ever recorded and the fifth wettest month ever recorded across the UK.
So with this, we can close today's session. First thing, what we have to understand from these videos is, you think like maybe it is not raining here, it is drought and so on, so kind of situations. It's not just local behavior. It is something to deal with, especially for Indian continent. Recently, people figured out this IOD is the most crucial role plays in terms of whether you will have drought or not. and just thinking like locally, I'm going to simulate this, what is happening and so on, so thing, one may not be even in a position to really understand what is happening. There's a lot of terminology going on. I'm not saying that each and everything we will just mug it up and learn it, but it's more like storybooks, which first of all, we will have little bit attachment to that. It's such a complicated science. Can we really make sense out of that complicated science? Maybe the time when we really go jump into mass, perhaps we make hundreds and thousands of assumptions, making it way beautiful. It looks like, wow, I'm solving a lot of complicated equations with so and so kind of thing. It's giving me new results. That's wonderful, but at the same time, we should really aware of what kind of approximations we are making on such kind of systems. With that, we are closing.